The derivative, what is it? Okay, there are some synonyms with the derivative. One of them is, well, before I get there, sorry, I was out of order. Okay, first of all, a tangent line. If you remember back to geometry in your circle unit, a tangent line only touched the circle once. Okay, now that we're going to apply this to all curves, a tangent line only passes through our curve once. One of the synonyms for our derivative is the instantaneous rate of change. Okay, we can talk about rate of change on a line, right? And we have a constant rate of change if we have a line. But if we're talking about curves, our rate of change is different at each point. Okay, so the derivative describes the instantaneous rate of change for a curve. Okay, and to find the instantaneous rate of change, we find the slope of the tangent line. Okay, so now we have two synonyms: instantaneous rate of change, which is the same thing as the slope of the tangent line. All of these things mean derivative. Are you okay? Mm-hmm. Okay, so the derivative is the instantaneous rate of change, which is represented by the slope of the tangent line at that point. Okay, so I'm going to draw you a nice little picture here. I'm going to put up a curve with a line going through it, hitting it twice. Okay? Now, as we bring these 2 points closer and closer and closer and closer together, we're going to get so close that it's going to become the, what kind of line? The tangent line, right? If I bring 2 points closer and closer and closer together, eventually we can get them so close that it becomes a tangent line. It's only going through once, okay? So look at this limit. The limit as x1 approaches x of 0. As we bring these 2 points closer and closer together, okay, this is the slope, okay? The instantaneous rate of change is the slope of the tangent line. So if we take the limit of the slope between these 2 points, as these 2 points get closer and closer and closer together, we will actually find the slope of the tangent line. Okay, so I'm going to give you a little visual. Are you ready? Watch as x of 1 approaches x of 0. Okay, everyone take a break and watch. As x of 1 approaches x of 0, as we get closer and closer and closer, we approach the tangent line. Okay. This is why we had to do limits. Okay. Now, let's talk about something that you're very familiar with. Do you remember this? Does that look familiar up there? F of x plus delta x? Vaguely? Not vaguely. Okay, so same picture. We still have this line going through twice, but I changed our notation here, okay? Instead of x of 0 and x of 1, I have x and x plus delta x. Delta x just means change in x, which means the difference from here to here. So if we're at x, oops, then this point is delta x. Okay? And then we have the y value for x and the y value for x plus delta x. Okay, so this is that same limit except with the notation that we saw back in unit 1. Okay, so this is still the slope, y minus y over x minus x. We just notate now with change in x. Okay, so we're still taking the slope, and as we bring x and delta x closer and closer together, we are going to approach that tangent line. Okay, so all of that work you did when you found these limits, you didn't even know what you were finding, right? What you were really finding was the derivative. Okay. As we take the limit, as those 2 points get closer and closer together, we found the slope of our tangent line, which is the derivative. Okay. This is how we notate it. F prime of x means the derivative of f. Does anybody need me to go through that animation again? This is the slope through 2 points on our curve, and when we take the limit, we're taking the limit as those points are approaching each other, which means we're finding the slope of now the tangent line, okay, which is our derivative, okay? It is vital that you know all of these terms. The derivative means instantaneous rate of change, which also means the slope of the tangent line, okay? So the derivative is giving you the slope of a tangent line at a point, or we can say the instantaneous rate of change at a point on our curve. Those words will become your best friends, okay? You know how to use them interchangeably. All right, so we are going to find the derivative of x cubed plus 1. Are you ready? Our derivative is just the limit of the difference quotient, which, good news, you've done before, right? So let's remember how we do this, okay? F of x plus delta x plus delta x cubed plus 1, minus f of x all over delta x. If you want to use h like you did in unit 1, that is fine. It's still going to mean the same thing. And you might see, sometimes you'll see h and sometimes you'll see delta x, okay? So x plus delta x cubed. I remember from back, remember Pascal's triangle gives us the coefficients for multiplying out a binomial? Do you remember that? Kind of. You can either multiply this out or remember that this is going to be x cubed plus 3x squared delta x plus 3x delta x squared plus delta x cubed. Plus 1 minus x cubed minus 1. What cancels out? The x cubed. Anything else, Cole? Yes, because I forgot to write something in too.
Oh, the ones.
The ones cancel out. I wrote plus and then I left it blank. I'm not sure what I did. Because there's plus 1 and then minus x cubed minus 1. So the ones cancel out. Okay, with what's left over, what should we always be able to do with our numerator? Okay, factor out an h, or in this case, delta x. Okay. Our delta x's can cancel, and now we can actually evaluate our limit. So f prime of x, we'll wait here. So if we plug 0 into delta x, we get 3x squared plus 3x times 0 plus 0 squared. So we're left with 3x squared. Our derivative, which we notate f prime of x, is 3x squared. Now, luckily, you've practiced the limit of the difference quotient before, so really the only new thing about today is you know now that it represents the derivative, okay? At any point on x cubed plus 1, the instantaneous rate of change is 3x squared, okay? So if, if we were talking about the point 1, 2, okay, I know that if we are talking about the point 1, 2, then the instantaneous rate of change at 1 would be 3 times 1 squared. The slope of the tangent line at x equals 1 is 3. Okay, which would be different than the point 0, 1. Okay, at 0, 1, which lies on this curve, x cubed plus 1, if we look at the derivative at 0, 3 times 0 squared is 0. The slope of the tangent line at 0, 1 is 0. Okay, so these are all going to have different slopes, right?
So the derivative doesn't technically be a line.
Right, so your derivative, more times than not, will be in terms of x, and it's representing all the different tangent lines at the different points, okay? So to evaluate what the slope actually is at those points, you would have to plug in x values to see what they are. Does that make sense? Okay, does that kind of give you a better idea of what that's representing?
I was thinking, like, if you had a odd function, technically you would think if you had a single line or something, you would take a function somewhere with that line. So.
Right. So these represent the slopes of the tangent lines, okay, but they're all different depending on which point we're at. Okay. All right. Now, we've done a lot of problems like this. You just didn't know what they are. Okay. So it kind of feels like, we know how to do this a little bit. Let's talk about differentiability. Okay. If a function is differentiable, that means the derivative exists at that point. Okay? We are differentiable here because we do have a tangent line that we can draw there. A function is differentiable if the derivative exists at that point. If we can draw a tangent line there, and only one tangent line, okay, there's only one tangent line per point. If we can draw a tangent line, then our curve is differentiable there. Okay. So what I'd like you to do is talk in your pod for about 30 to 60 seconds about a kind of graph that maybe you wouldn't be able to draw a tangent line at a point. Okay. What would it look like if we weren't differentiable? Have a conversation. Okay? Any ideas?
Cosine and sine graphs.
What about them?
Well, like it just keeps going on, so I don't think there's just a way to draw one line and only go through one point.
When you think about tangent lines, don't think about them going on forever. Just think about drawing like small ones, because it is possible for a tangent line to like hit later on, right? If our curve is crazy, just think about drawing like if they were only like this long. Does that make sense? Cosine and sine are actually safe. They are differentiable everywhere. Okay, but I see what you're saying. That was a good thought. Pod 6, you guys are talking about something. No?
The odd function, I think we just get twice.
Okay, you're kind of thinking the same thing as Logan. Just think about drawing like little tangent lines. Don't worry about what happens like when you draw them really long. Okay? Where would we not be able to draw a tangent line at a point?
Straight line.
Okay, what kind of straight line? Okay. If we have any, what I was trying to get you to say is vertical, okay? If we have any time where we're going to have like a vertical tangent, what's the slope of a vertical line? Okay, it's undefined. Our derivative represents the slope. If our slope is undefined, the derivative is undefined, okay? That's what I was trying to get you to say. If we have discontinuity, can we draw a tangent line there? No, if we have discontinuity, we cannot be differentiable. Or if we have a corner, okay? At this corner, there isn't only one way to draw a tangent line. Okay, I could try to draw one this way, I could try to draw one this way, I could try to draw one this way. There's no like one way to draw a tangent line. It's not going to work. Okay. These are the 3 times where we will not have a derivative existing at that point. We call it non-differentiability. Kind of a mouthful, isn't it? Okay. So, anytime you see these 3 things, we are not going to be differentiable at the point that I'm describing. Okay? Let's look at some more pictures. We are not differentiable at 0. Why? We have a corner. We're not differentiable. Okay? We are not differentiable at 0. Why? We have a vertical tangent line. Okay? Okay. Here's something that's very important. If f is differentiable, then we know it must be continuous. If it's differentiable, then it has to be continuous. "30 seconds, talk with your group." Is the other way true? If it's continuous, is it differentiable? All right, Pod 1, what do you think?
No. It can be continuous and still be different. Or non.
Can you give me an example?
Like the one with the vertical line.
Okay,
It's continuous, but there's an X that's not.
good, okay? It's not true the other way around, okay? You described the vertical tangency example. I have up here a corner example. This is continuous, but since there's a corner, it's not differentiable. All right, here's some notation for you, okay? F prime of x. That is what you've seen for a derivative. You may also see y prime. Okay? Both mean the same thing. Okay? You will also see dy dx a lot, basically standing for change in y over change in x. Okay, slope of the tangent line, dy dx. Along with that, this means please take the derivative with respect to x of this function. Okay, those are the 4 different notations you're going to see for now. Okay, so I will tell you right now, you are going to be writing a lot of tangent line equations. Okay, it's what we're going to use to approximate values later, but it's just going to happen. You're going to write a lot of tangent line equations. So that's what I want to practice. You know what? Okay. We're going to start with this. We're going to take a function and we're going to evaluate at a point, and then we'll talk about the tangent line equation. Okay? So our curve, y equals x squared plus 1, and I want to evaluate it at the point 310. So I'm going to use one of our alternate notations. Dy dx also means derivative. Okay. Is the limit. Do you guys want me to use delta x or h?
H.
Okay.
So you
I will use h. So we have f of x plus h, which looks like this, minus f of x all over h. Okay, x plus h, the quantity squared. Plus 1 minus x squared minus 1. All over 8. Okay, so we should get things to cancel at this point, correct? What cancels? X squared and 1. We can then factor an h out. So our h's cancel. Then what do? Plug what in? 0 in for h. If we plug 0 in for h, we're left with 2x. Our derivative is 2x. Okay. Now what I want is for us to evaluate our derivative at the point 310. 310 is a point on this curve. Okay. So let me show you a little bit more notation. If we write dy dx, this big slash bar means evaluate. Have you seen the evaluate views on science? I don't know. Okay, this means evaluate at 310. Our derivative evaluated at 310. That's what that notation means. Okay? When we plug in x is 3, what do we get for our slope? 6. So the slope of our tangent line is 6. So if I were to ask you to write the equation of that tangent line, remember I told you slope, point slope form, that's what I want you to use. Y minus y equals slope times x minus x. And this is how I want you to leave your answers. It will help us when we're using these to approximate later. And that's it. Fantastic. Okay, biggest thing about today, you have some new notation. You now know what a derivative means, and you know where a function can be differentiable. Okay. On Monday, we will still work in this section and talk about like the relationship between a graph and a derivative graph. Okay. Let me stop the recording here.